Welcome to Going Antiviral, the podcast for the IAS-USA, a professional continuing medical education organization focused on HIV and other viral diseases. I'm Dr. Michael Sagg, professor of medicine and infectious diseases at the University of Alabama at Birmingham and volunteer member of the IAS-USA Board of Directors. Welcome to the Going Antiviral podcast. Today, March 4th, 2025, we are speaking to Dr. Joseph Iran, a professor of medicine at the University of North Carolina. Dr. Iran is a principal investigator for the NIH-funded UNC Global HIV Treatment and Prevention Clinical Trials Unit and an active investigator in the AIDS Clinical Trials Group in the HIV Prevention Trials Network. His research focuses antiretroviral therapy for the treatment and prevention of HIV infection and on novel clinical interventions to impact the HIV reservoir and enhance HIV-specific immunity. Today, Dr. Iran joins us to discuss the topic of his upcoming presentation at CROI 2025 as part of the Scott Hammer Young Investigator Symposium. His topic is HIV cure research, state-of-the-art, and navigating presentations at CROI 2025. Joe, welcome to the podcast.
Hey, Mike, it's great to be here, and thank you for inviting me to talk to you today. It'll be fun.
Well, we've been meaning to talk about cure, and this was a great way to bring it up, and you're the perfect person to go over this with us, especially with your upcoming presentation. But let's take a step or two back.
Sure.
What do we mean by cure?
Yeah, it's a great question. There are two basic ideas behind cure. One is kind of cure in terms of a classical cure, meaning all HIV that can reproduce itself is removed from the body. And we can talk about that because there are examples of that have happened, which are some of which are quite famous now. But the thing that's a little bit more likely, I think, that could maybe impact a much broader population is what we're calling functional cure. And that's where HIV remains completely suppressed in the absence of therapy. HIV might not be completely gone from the body, replicating HIV, but it's been securely controlled by the patient's immune system or by kind of locking the virus down.
Yeah, I want to get into that in detail in a second, but just to kind of recap for folks, Timothy Brown was one of the first people cured. He was also known as the Berlin patient, had a bone marrow transplant for an underlying malignancy, and for all intents and purposes eradicated the virus from his body with that fairly aggressive chemotherapy and bone marrow transplant. And there's been several other patients since then, usually assign the name of the city where the cure happened, like the London patient, et cetera. And that's a pretty aggressive model that people have underlying cancer. Are there any other cures that you're aware of that did not involve a patient with cancer who got a bone marrow transplant?
Yeah, that's a really good question, Mike. And I think, first of all, there are now 7 well-documented cases of people that have gone through these transplants for kind of cancer-related, these stem cell transplants. And there are actually a couple of more presentations at CROI that look, very suggestive. And we'll see those posters as the meeting goes on. But actually, someone that we can say 100% has been cured without that. There is an intriguing patient that was described, I think actually 2 years ago now, from Brazil, that appears to have been cured through an intervention. We haven't heard a lot more about that participant yet, but there are these kind of very interesting elite controllers where various groups, but predominantly Matthias Lichterfeld and Shu Yu at the Broad in Boston, where they've looked at a couple of elite controllers and gone through the same test that like Timothy Brown went through and the London patient went through, and they can't seem to find virus in these people that can replicate. So maybe people are over time able to really fully control or even eliminate actively replicating virus, but like a specific drug or a specific intervention that does that, we don't have that yet.
So to set the stage for our discussion here today, let's go back to the basic biology, and I think people get confused about mostly why is it so hard to cure, and maybe you could review uh, what's happening in the body when someone gets infected and why we can't fully eradicate the virus with antiretroviral therapy itself.
Yeah, that's such an important question, Mike, and one that I think confuses people living with HIV that come into care with us. And but the main issue is that part of HIV's life cycle is kind of revving up and destroying T cells and driving immunity down low, and what we call AIDS. But part of the virus life cycle is to get into the human DNA and become latent. And latent is sleeping within the human DNA. And these are in the CD4 cells, the memory CD4 cells. And those cells are meant to persist for a long time. So that's why we get a vaccine when we're a child to prevent measles. And if we're exposed to measles when we're 40 years old, it's prevented. It's because those cells remember. And the cells don't live for 40 years. They proliferate slowly. And if they have virus within them, this latent or sleeping virus, then that virus is going to persist also. And the problem is that HIV, when it's silent, it's completely silent. And the human genome is huge. The HIV is tiny, and it kind of inserts itself randomly, so you can't pick it out in a spot. So that's really the basic problem. It gets into cells whose job is to persist for a long time. And when it's in those cells and sleeping, it's really hard to find it.
Exactly. And just to complete the picture, when we give antiretroviral therapy like an integrase inhibitor or a nucleoside combined with that, what we're doing is we're stopping the ongoing replication that's usually a wildfire prior to the initiation of that. And then once that wildfire is brought under control, these latently infected memory cells are kind of like embers of sorts that if we ever stop the antiretroviral therapy, the fire reignites and they go right back to high viral load. Is that
Exactly
fair?
right. I think that's exactly right. And I think what we don't know is what's the ignition? Because they really are latent and sleeping. And, one example is the Mississippi baby that we talked about 10 years ago, or even a little bit longer than that stayed off therapy for a long time. And then something happened and the virus rebounded. So that what sets off that sleeping cell to start producing virus. But they're there. They're like small time bombs that can take
Yeah,
off, just like you
reignite.
said.
Right.
Reignite. Perfect.
So we understand then that uh, an actual cure, or however we want to define it, like with a bone marrow transplant, everyone gets that. You get rid of all those memory cells
Right.
through some form or function, and then they're just not there and the virus isn't there. But then you mentioned this concept of functional cure. What does that mean exactly?
Yeah. So functional cure means that those cells that we're talking about, they're not gone, but they're controlled. And they could be controlled in two ways. One way is that we kind of improve people's immune system so that as soon as those embers start to crackle a little bit, the immune system shuts them down. So that's one way. The other way is this really different idea that over time, maybe the virus can get kind of trimmed. So it's only in parts of our DNA that's essentially locked down, so that they're so locked down that they can't reignite. And those are two ways that we might be able to induce kind of a functional cure. And one step might be to decrease the number of those cells, right? I mean, if there are millions of them and we could actually get rid of, 100 times down, get down to thousands of them, maybe the immune system could do a better job of controlling. So there's all these different strategies to try to knock down those cells, control them from reactivating, and maybe even lock them down so they can't reactivate.
Yeah, and I'll just speak from first person, 10 years ago or so when we seems like we realized that we're not going to get all that many actual cures, at least at that moment in time. And we sort of segued over to looking at functional cures. And a lot of the early attempts were looking at ways to rev up the immune system or
Yeah.
find a way to stimulate it so that without antiretroviral therapy, the immune system would keep it under control. But my concern was that if we really relied heavily on the immune system day in, day out, that would be kind of exhausting and also probably be associated with some sort of inflammation, sort of defeating the purpose of not using antiretroviral therapy. It sounds like things have progressed in the functional cure space to something more exciting and beyond just theoretical, actually some opportunities. Can you go into those things a little bit?
Sure, sure. And Mike, I think you brought up a super important point that we shouldn't skip over too fast. If suppressing the virus requires constant immune activation that may lead to things like heart disease, liver disease, kidney disease, that's not what we want, right? So you're exactly on top of it. So a couple of things we've noticed. One are these broadly neutralizing antibodies. Now, we know that antibodies aren't good at controlling HIV, but there's clues where people living with HIV who have virus replicating get one of these broadly neutralizing antibodies. Somehow, those people actually have control of their virus after that happens. So it's as if these broadly neutralizing antibodies are somehow stimulating the immune system. And we know in animals like macaques, monkeys, it may be that somehow the antibody, mixed with the virus leads to almost like a vaccine response. And so we also know, Mike, that some of those elite controllers that we were talking about control the virus without any excess immune activation. So that's what we're after.
Yeah. And we know also that we use IVIG, not broadly neutralizing antibodies, all the time to sort of have magical effects for a lot of diseases. Just give it, no, look, they're better. And so maybe there's something with the FC portion of the antibody, of a broadly neutralizing antibody we got to learn more about. Maybe that's involved, or maybe it is the business end of the antibody with the AB portion. But regardless, it is an exciting pathway. Talk about some of the other approaches besides broadly neutralizing antibodies, the block and lock and that type of thing.
Yeah, so block and lock is this idea that there are parts of our human DNA that are kind of locked down, that where the genes are not expressed. And one way to think about it is a substantial proportion of our human genome is actually kind of old retroviruses that we were infected sometime from when we were like tadpoles all the way up to as humans. And those viruses are in our system, and many of them are locked down. So the idea here is to try to come up with a way that you can stop HIV from activating. And people have done it in the test tube. People are starting to do it in people. And it looks like even someone who's been on therapy for a very long time, at least some proportion of those people appear to be locking down their virus. Their virus gets into these areas of the genome that really don't express virus very well at all. And it's probably what's happening is the viruses that are susceptible to the immune system that are activated, those embers that you talked about, are being put out, essentially. They're being extinguished. And then the virus that can't activate is the only thing that's left. And there's some really exciting data that was recently published that maybe children or people with HIV infected when they were children and have been on therapy for a long period of time are actually able to do that, able to completely lock down the virus. And I think we're going to see more examples of that, of these people treated when they were young, maybe when their immune systems are healthier, more robust, they're able to lock down that virus. So I think that's another major step. And then there's some stuff that's kind of really in the earliest kind of forms of exploration that we could talk about if we have time.
Yeah. So to dig a little deeper on this lockdown,
Sure.
part of the reason that HIV is such a aggressive virus is that it has regulatory genes that it expresses, something called TAT, that can stimulate it, and then in its so-called long terminal repeat in other parts of the virus, that can get the virus to begin to express. And you asked the question earlier, or alluded to it, about, well, we don't know exactly what might stimulate an embryo to come out, but it does seem like activation of T cells, that they're in some sort of that activation, stimulates the virus to start producing, especially TAT and other things. And I was noticing that there are some approaches to block TAT as a way of perhaps creating that lockdown
Right.
situation.
Yeah. Yeah. So that's a fascinating story. So TAT is like an accelerator of replication, right? When the virus starts to make its RNA from our DNA, kind of that reverse transcription step, when TAT gets involved, it kind of speeds up the process and really kind of get things going. And you might recall, maybe even 15 or 20 years ago, it turned out the first TAT inhibitors actually um, engendered quite a storm, a cytokine storm. And what we have now are things that are a little bit more surgical, that are kind of binding to TAT in a way that blocks it a little bit more effectively. The problem is that the molecules that do that are not yet ready available. They're not ready to be given to humans, in part because they're chemically very structurally complex and difficult to manufacture. But the idea is there. If you can stop TAT from accelerating the process and give the host, the human, machinery that kind of locks things down, that brings in that chromatin, that gets rid of the acetylases and as the methylases and things that really stop that from getting ready to spark that ember that you perfectly kind of outlined before, that can make a difference. So these TAT antagonists, it's a very, very aggressive area of research, but it's complicated because those molecules are hard to manufacture.
Yeah, and then you have to make sure that they stay on board for a long time, or maybe
Right.
even permanently inactivate the TAT, so you don't
Right.
have.
I think that's right, Mike. I think the idea that we're just going to trade one pill for another, it's really about block and lock. If we don't get the lock part, it doesn't really get us where we want to be, right? We want it locked down so there isn't a medication that we're taking, for a lifetime, because we got that
Yeah.
already, and we know how safe our antivirals are, or relatively safe compared to all the other medicines that many people have to take. So that's a really important point. It's block and lock. And that's where I think we're learning that lock is actually possible. I was totally skeptical, honestly, but I think lock is actually possible.
Yeah.
But we're a long way from there for lots of people.
The other area I wanted to make sure we got to was the notion of, for lack of a better word, molecular scissors. The
Sure.
ability to go in and surgically, very surgically, precisely find the viruses, those, I think you called them straws in a haystack, needle in a haystack, but straw may be more appropriate because it
Yeah,
is part
straw
of
in a
DNA.
giant straw stack, right?
Yeah, and but can go in and find that one area, and these CRISPR-Cas9 sort of scissors, molecular scissors, can clip either the whole virus or even a critical part of it,
Virus.
excise it, reunite the DNA so that virus is no longer viable. And if you did that to all those existing integrated viral DNA constructs, you'd have a cure.
Absolutely. And I think, that's an idea. And there are, animal models that are being tested. There are a couple of abstracts at CROI that get into CRISPR-Cas. The problem is, how do you get this kind of enzymatic interaction, which is what CRISPR-Cas is? You've got the guide to get to the right sequence, and then you have to then chop it out, like you said. So how do you get that inside the cells? You can't obviously swallow it; it would be digested. So I think that, and so people are creating, lipid particles, maybe lipid particles that have, CD4 on the surface to bind to infected cells, ways to get that mechanism inside a cell. So I think, you know, that's a big challenge. But again, we've had really big challenges before and we've overcome them. So I think that's one idea. Another idea that's also going to talk about it quite well, can you kind of instead of having to have cancer and get a stem cell transplant, can we re-engineer people's cells without a stem cell transplant so that they're immune or resistant to HIV? That's another idea, that you can do genetic modification of cells, and then those cells will then kind of populate in a person. And that's, again, almost science fiction, but I think we're getting closer to those options.
And it feels like with the molecular scissors or CRISPR-Cas situation, that it's not going to be just HIV using or trying to use that technology. Any genetic disease,
Sure.
right? From sickle cell to any,
Yeah, no, sickle cell, it's being done, right? I mean, there's an approved cure for sickle cell. The thing is, you know where that gene is, and you know exactly what the genetic mistake is. And the problem with HIV is that it's kind of randomly inserted. And sometimes it's actually inserted in a gene that might actually be important. And then if you disrupt that gene, it could have a toxicity that you don't expect. So I think it's, and again, it's not, we're not sure it's completely random where HIV is, but it's certainly not in one specific spot. Some viruses, integrate in very specific areas, but in this case, that's not the case. So I think, this idea of excising harmful genetic material is going to be kind of everywhere in our medical lexicon over the next, decade or so. But for HIV, it'll continue to be a challenge, and you have to find all of them. That's the problem. Right. Like the Mississippi baby, they probably got almost all of them. But if you don't get the one and it meets its cognate antigen and that ember ignites,
then it's all game over. It's back. And one other thing to round that out, and then I want to get to CROI. But I remember, I think it was Chip Schooley years ago when CRISPR-Cas9 technology was being discussed. He wrote an editorial that said, "Running with molecular scissors." We're taught not to run with scissors because you could slip and fall and cut something that you didn't intend to, and that could really screw things up.
Yeah, right? Chip is almost as clever as you are, I would say, because that is really perfect. Yeah, you don't know where when you know exactly where the scissors are going to go, like in sickle cell, for example, it's one thing. When your scissors are going to be like maybe cutting all over the place, it's an issue. But people are clever. Science is important. Science is important. We're going to say that 1,000 times at CROI. Science is important. And exploratory research, it's so important, because we're not going to get the next big thing unless people try to do the next big thing. And it takes, people that are creative, people that take, are willing to take a chance on an idea. So without science, we're in trouble.
Right. Well, let's finish up our conversation talking about science at CROI this year, and let's focus on the area that you're going to be talking about with regard to cure. I noticed that there's a bunch of abstracts talking about a lot of the things we just discussed. What do you see coming out? What you would be looking for at the meeting?
I think there's more data on how people control, right? When we know that some people, lead controllers, there's also something called post-treatment controllers, where they stop treatment and they seem to control. And there's several posters on that. We're going to hear from the Rio trial, which is another trial of giving these broadly neutralizing antibodies. And there's been some exciting rumors about, post-treatment control in those people. And I know there are abstracts trying to get to the bottom of how is it controlled? What are these antibodies doing? Are they really making the immune system better somehow? I think that's going to be exciting. I mentioned a couple more of these stem cell-like potential cures. And we're learning about these other cells that might be important, like natural killer cells or NK cells, that may be the first patrol that is spotting those embers. And maybe we need to wake those cells up to really extinguish those embers before they get going. So I think there's so much stuff at CROI, so much good cure science. I don't think there's the home run yet, but I think the body of knowledge at CROI this year is really fantastic. And I got to say right now, Ole Sogard is giving the first plenary, and he is fantastic. And it's the plenary on Monday morning, and I honestly cannot wait for that plenary. He's a superstar.
Well, our time is up. We covered a large amount of ground here. This is fabulous. And I think obviously Jim generated a lot of enthusiasm for what's going to be coming out next week at CROI. I'm excited about it. I know you are. And I think if folks, even if you can't participate in the meeting, even if you're not going, that the abstracts will be released roughly about the day that they've been presented, and then the presentations will be available to everyone about a month or so after the meeting. So even if you don't attend CROI, you can still access the information. The purpose of the meeting is to share scientific knowledge, not to restrict it. And the platforms that have been created for the meeting are very accessible. We will continue to send out information about how to access all this, but I think it's a way that folks in the community, but also scientists around the world who can't attend the meeting or even didn't register for it will be able to have access. And that's a key contribution of CROI over the years, and that will continue.
Great. Thanks, Mike.
Okay. Thank you, Joe. That was a wonderful review, and look forward to seeing you next week.
Great, Mike. I will look forward to seeing you too. Thanks for all you do.
Thank you for listening to this episode of Going Antiviral. Catch up on earlier episodes wherever you listen to podcasts, and check out the video versions of this episode and others on the IAS-USA YouTube channel. You can find these links in the show notes, or simply go to YouTube and search for IAS-USA, and there they are. Be sure to subscribe, rate, and review Going Antiviral on Apple Podcasts. This podcast is for informational and educational purposes only and is not intended to serve as medical advice. Opinions expressed in this podcast do not necessarily reflect the opinions of the IAS-USA or its affiliates. If you have a question you'd like answered on the show, you can send it to podcast@iasusa.org to be answered in a future episode.